Hello and welcome to the fifth lecture in chapter 22 of our comprehensive course in artificial intelligence, machine learning and data science. In this chapter, we are doing various tasks relating to data pre-processing or feature engineering. And in part A, we have done feature creation, creating new feature, right? Then in part B, we are at present doing this part, data scaling and normalization, in which we have already done standard scaling and min-max scaling. So that means only one thing is now left in this part B. We have already done these two, okay? And now what is left is normalization. Now what is normalization? When I do this part, this much, and even this code, and then this code, then things will not become 100% clear, and that is perfectly all right. But as we do this lengthy discussion, you can see thereafter we will take another code which will be much more detailed, this one, and then you will get perfect understanding of what normalization is. So don't worry, just try to hang on when I am doing this part. So normalization adjusts the measures of the feature so that they are measured on same relative scale. Now this looks like this only, right? That is this min-max scaling or this standard scaling, because if you remember that in this min-max scaling, we did somewhat like this way, that we imported these libraries, and this is my data frame, not this one, but rather California data I want to talk about. So that is this one, right? And fetch California housing somewhere I will have to import earlier. So that is there from the sklearn library, okay? So it was imported far earlier. That's why today I am restarting my kernel. So yeah, this is from sklearn.datasets import fetch underscore California underscore housing. So once you fetch it, then you can load the data, and once you load the data, then you can view the data, or you can view the statistical summary of the data using that describe, okay? But before that, let us load. Now this is the statistical summary of just one column, and if I do this way, then that would become the statistical summary of entire data set, and that explains what is the meaning of this sentence. That normalization adjusts the measurement of features so that they are measured on the same relative scale. So it looks like that in min-max scaling and standard scaling also we were doing the same thing, right? So that was this had minimum value this 0.49 and the maximum value 15. This has minimum value 12 and maximum 52, so more or less same. This had 2.4 and this had 141, more or less same. But these or even the bedroom is also same. But this population, its minimum value is 3 and the maximum value is 35682. So that means various columns or features, they are not on same scale, and therefore after normalization, if you do, then you can get all of them on same scale. Okay. So it looks like that what is new in this min-max scaling, standard scaling were also bringing the features on same relative scale. And here in the normalization also, it is seen that it brings the feature on same relative scale. Then what is the difference? There is a big difference between min-max scaling, standard scaling and normalization. That is why though some books and some tutorials prefer, not prefer, but they often use min-max scaling is equal to normalization. But I strictly insist that you use the word min-max scaling and standard scaling only for that scaling process which we have done so far. While normalization we will reserve for this case which we are now discussing. So it adjusts the features so that they are measured on same relative scale. How it adjusts? These often involves dividing the numerical attribute by some measure of data scale like Euclidean length of feature vector in the feature space. As I said, when I do all these things will not become clear. So just hang on. So that means every observation is divided by Euclidean length of the vector. But as soon as you read this word vector, things should become clear that normalization uses some number for dividing numerical attribute, but that attribute is calculated row wise and not column wise, right? So that means here, if I write this for example x and y, this data frame, then for standard scaling we do this kind of thing, right? This was our formula for min-max scaling, for example, that x minus minimum of x and maximum of x minus minimum of x. That will give the normal value, and that means each observation, which was originally 246, will be divided, will be converted into this form: value of that observation minus minimum of all the observation divided by range of x. That is maximum minus minimum value of this observation. Then we get this kind of this list, and we say that x has been normalized. Okay. That is x has been converted into min-max scaled version of x, and that is called zx. Okay, but here this minimum value and this maximum value, all these are found from the column x. So that means that this is x, Then where is x minimum? Then x minimum you have to look in vertical column and you can find that 2 is the minimum value. So that is x minimum. Where is x maximum? Then this 8 is the maximum value. And then you have to use that value for calculation here to find the normalized values of x, okay, or that is the min max scaled values of x, okay. Now similarly in the standard scaling it was different slightly. We don't do x minimum and x minimum maximum, but at that time we do somewhat like this, that this was the case, that any observation minus the mean value divided by standard deviation. But mean value of what? Okay, then mean value of that column, okay. So that means that if I say that this is my column x, then observation is 2 minus mean of all these values in the x column, vertical column like this, and divided by standard deviation of all these values in the y column, right? So that is what you do in the standard scaling and min max scaling. In short, whenever I am scaling one particular column, I remain confined to that column only. I don't use any value from y column or z or x, p column or q column, other columns, right? I just use minimum value, maximum value, mean value, standard deviation, whatever is used for the calculation of the standardized value, that is from this column x only. Similarly, if I am calculating standardized values of y, then all minimum, maximum, mean value, standard deviation will be from this column only, 1000, 4000, 3000, like that. While here, if you read the sentence carefully, then it says that it adjusts the features, measurement of features, so that they are on the same relative scale, but it often involves dividing the numerical attributes by some measure of data scale, like the Euclidean length of vector in the feature space. Now, vector is never a column, vector is a row. So that means that this is applied row-wise. That is the biggest difference between min-max or standard scalar and normalization, right? So now in normalization, we will calculate the Euclidean length for 0th row, Euclidean length for first row, Euclidean length for this second row, and then we will divide each observation by of 0th row by Euclidean length of 0th row. Each observation of first row by Euclidean length of first row, each observation of second row by Euclidean length of second row, like that. Okay, so I hope that that is clear, that what the most important difference between normalization and min-max or standard scaling is. Min-max and standard scaling are applied column-wise, while normalization is applied row-wise. Okay, fine. What is Euclidean length and all that? You don't worry at present. That's what we are going to explain. So most important feature between the two scaling and normalization is that normalization depends on row-wise calculation, unlike scaling, which depends upon column-wise calculation. Okay. Now let us do L2 normalization. That is for Euclidean length. Again, I fetch that California housing data set, and this is my data frame. I am just printing only one column, say average rooms column. I can select any other column also, so that is also fine. Now, just like for standard scaling, min-max scaling, what was the code? From sklearn.preprocessing, import min-max scalar. Okay, M and M are capital and S is also capital. Similarly, from sklearn.preprocessing, import standard scalar. Similarly, here from sklearn.preprocessing, import normalizer. Once normalizer is imported, thereafter the steps are saying that create a normalizer object. So normalizer object, here you can give any name, A, B, C, this is just a name which you have given, is equal to normalizer which you have imported with norm equals L2. Now this L2 is, what is L2, don't worry at present, but this L2 is the default norm. So that means even if you don't specify it, then also it will automatically take L2. There are three norms possible, L2 or L1 or max. And what are the differences between the three norms, that we will see very soon, today only, in this lecture only. So let us write, we have created an empty normalizer object and apply that normalizer object. This is what we have been doing everywhere throughout this chapter, that normalizer.fit_transform, and in bracket you write either entire data frame, then it will be applied to entire data frame, or you can write to one particular column of the data frame, then it will be applied to one particular column. Now here I am writing to average room, right? So there, this is average rooms. So I will here also make average rooms. Those who have printed notes, they will find house age. So that is fine. Any different columns can be taken. So if I do this, then you can now see the difference between these and this. Okay. Now here there is absolutely no change in this particular value. So that shows that the average rooms column was already normalized right from the beginning only, and therefore after doing normalization, no change occurred. Every time it is not necessary that this will happen. So we will see that, and that is the reason I told you that this much when I do, things will not become fully clear, but you can at least understand this much thing, that standard or min-max scaling, there when you do xi minus mu divided by standard deviation, or xi minus minimum value divided by maximum x minus minimum x, then all those calculations are done for a given row, given column. While for normalization, we will do calculate Euclidean length for each row. Okay, let us see now in more detail. First, what is the Euclidean length and what is the another type of distances? In this data science, several types of distances are used between 2 points. For example, if the black and red are two dots, then simplest join them, that is called Euclidean distance, right? then instead of that, you join them this way. First move only on horizontal axis and then move only on vertical axis, or that is x axis and y axis. So then this length is called, this is called Manhattan distance between the two. Similarly, instead of measuring the distance, you can measure the angular separation also, because distance is also ultimately measuring how separate the two dots are, right? So you can measure angular separation also. So that means if this is black dot and red dot and someone says find how far away they are from an angle perspective, then you can select one point as the origin and join both black and red dot here, and whatever angle is made, that is called cosine similarity. That is a measure which is used for cosine similarity. Cos of this angle, cos theta, that is called cosine similarity. Because for that, you know why similarity word is used, because cosine is a decreasing function. That is, as theta increases, that is as the two points become further and further apart in the angular manner, cos theta decreases. So that means that from similarity perspective, they become more similar as the angle increases, right? So then in that case, we use cosine similarity. There is something called Minkowski distance and Chebyshev's distance. In addition, these are also there, Hamming and all that. But if you see application of this Hamming, then Leveshin, and Jacquard, and this last one, then you can see mostly they are useful for bioinformatics, DNA sequencing, then string similarity, then this is Jacquard is used for text recommendation system. So that is one important thing. But this ecology, biology, genomics, etc. But at least Euclidean, Manhattan, and cosine similarity, these three should be clear. So here we want to do about Euclidean and Manhattan distance. As I said, these are 2 points A and B, right? And here this distance, horizontal distance, is x and the vertical distance is y. Then we know that this is the red line is the hypotenuse of the triangle, and therefore what will be the Euclidean distance? Then Euclidean distance would be under the root x square plus y square, right? And what will be the Manhattan distance? Then that will be this plus this. Okay, so Manhattan distance is simple addition of this plus this. Okay, and we want to at present talk only about Euclidean distance. So the Euclidean distance is x square plus y square. Where what are x and y? If any number is, if any vector, this is a vector from A to B, if any vector is expressed in terms of its x and y coordinates, then under the root x square plus under y square, that will give the length of that vector, right? If it is x, y, and z coordinates, 3 coordinates, then under the root x square plus y square plus z square. If there are 4 coordinates, p, q, r, s, then the length of that vector will be under the root p square plus q square plus r square plus s square. That will be the Euclidean distance. So with that much background, let us see now. Forget about the other differences at present. This I have just given as an extra knowledge. So if you don't follow everything in this, then don't worry. Okay. But how normalizer works? Then normalizer works. Apply normalization on rows. Here you can see the bold. So never forget that the calculation metrics are derived from the row and not from the column of the data set using specified norm. So normalized value of any vector. Vector, when I use the word, that means x and y, if there are there like this, then this 2, 1000, that is one vector. 4, 4000, that is another vector. 3, 3000, that is another vector for x and y, right? So normalizer is defined in this manner, that any value divided by the magnitude of that vector. Now how you calculate this magnitude of the vector, that defines 3 types of vector normalization. If you calculate this magnitude of x by Euclidean method, then that is called L2 normalization. If you calculate this magnitude of x as a simple sum of x and y, when I say Euclidean method, that means here what will be the Euclidean value of this vector? Then it will be under the root 2 square plus 1000 square, right? And what will be simple sum of these two? Only the mode. So if negative are there, then also you have to consider positive. So that will be 2 plus 1000. So then it is called L1 normalization. And if you consider the larger out of the two as the denominator, then it is considered the max normalization. So the 3 types of normalization, for them the numerator is same, a given observation in any row divided by some magnitude, but that some magnitude would be what? Then for Euclidean distance it would be under the root x square plus y square plus z square and so on. That is Euclidean magnitude. For that is L2 normalization. Then for L1 normalization, that would be the sum mode x1 plus mode x2 plus mode x3, mode x1 plus mode y1 plus mode z1 and so on. That is the sum of all the values in that horizontal row, and absolute values you have to take. And if third type of that is called L1 normalization, and the third type of normalization you take is the maximum value here of the entire row, and that is called max normalization. So if I take here, I can write normalized x, and what is normalized x? Then that will be 2 divided by under the root 2 square plus 1000 square. Okay. Then 4 divided by under the root 4 square plus 4000 square. That will be L2 normalized x. But if I write L1 normalized x, then what it will be? 2 divided by 2 plus 1000. That is 1002. 4 divided by 4004. 3 divided by 3003. Sum of the vectors observations. Okay, that is the vector elements, and it should be absolute sum or only positive magnitude you have to consider while doing the addition. And what is the max normalization? Then the value of the observation 2 divided by the maximum in that vector. Now this is the vector, so maximum is 1000, so 2 by 1000. What is the max normalization for this? 4 by 1000. What is the max normalization for this? Then the third row, then 3 by 1000, and so on, right? So that is how normalization is done. So let us take each normalization one by one, and you will see types of norms. One norm is called L2. In general, this is called norm, where observation divided by some magnitude. But how you define this magnitude, that is denominator, that decides three types of norms: L2 norm, L1 norm, and max norm. So norm is equal to L2, that is the default value. Then each row is scaled so that Euclidean norm is used. So x2 is equal to sigma xi square. For example, x is 3, 4, suppose, like this. Then L2 norm will be equal to under the root 3 square plus 4 square. And this is one row. Remember, this is now not one column. Okay. So under the root 3 square plus 4 square. And therefore, this vector 3, 4 will now be divided by this magnitude x2. So that, because that is the definition, you have to take each observation and divide it by the magnitude. So magnitude in L2 normalization is Euclidean distance. Therefore 5, so 3 by 5, 4 by 5, right? But if it is L1, so then it is Manhattan distance, and Manhattan distance is simple sum of the two distances. So 3, 4, and what will be the denominator? That is this mod x, then that will be equal to mod 3 plus mod 4, or that will be 7. So what will be each observation? 3 by 7, 4 by 7. Now, so when I convert 3 by 4, 3 comma 4 to 3 by 5 comma 4 by 5, I will say that I have L2 normalized this row. Similarly, when I convert this row to this 3 by 7, comma 4 by 7, I will say that I have L1 normalized this row. And you can see that the results are different, right? And similarly, max normalization is simply what you will put in the denominator, then the maximum of the value in the row. So this is one row, 3 and 4. So I will put maximum value is 4. So therefore, that will be divided, each observation will be divided by that. So 3 by 4 and 4 by 4, or that is 0.75 and 1. So that is called max normalized version of this x. So same row, 3 comma 4, or same vector 3 comma 4, if I apply L2 norm, it gives this answer. If I apply L1 norm, then it gives this answer. And if I apply this max norm, then it gives this answer. So that is why there are three different answers. Okay. Now this is just a summary of what you have done. So what is the scaling goal for each? That is important. This definition I have already explained. But in L2 normalization, each row becomes a unit vector. Now that is, if you see this, then this will be under the root 3 by 5 whole square plus 4 by 5 whole square. That is the magnitude of this. Let me calculate that, and it will be 1 unit. So you can see this is 3 by 5 comma 4 by 5. So if I find its magnitude, then it is under the root 3 by 5 square plus 4 by 5 square, right? And this 3 by 5 square is this 9 by 25. And this 4 by 5 square is this side 16 by 25. And therefore, if I add them, then it is 25 by 25, and that is 1. So this is actually unit vector. So the goal of L2 normalization is to make each row a unit vector. Okay. And therefore, this type of normalization is important in physics also many times. Then this L1 normalization, what is its goal? The absolute values of each row, their sum becomes 1. Now let us see. This is L1 normalized with the value 3, 4. After L1 normalization became this 3 by 7, 4 by 7. But if I add them, then it is again clear that 3 by 7 plus 4 by 7. Now ideally I should not explain that, because it is clear that it is 7 by 7, and therefore it is 1. So the sum of its magnitude of its vector elements, x and y elements, that is equal to 1. Okay. Then what is the goal of maximum max normalization? Largest value in the each row becomes 1. So that is why here it is 3 and 4. They were the value. When I applied max normalization, what was the largest value? Originally 4. That has now changed to 1. Okay. So that is what is the goal. This is important because that will help you to decide based on what you want to do with your data. Sometimes you want to convert each row into unit vector. Sometimes you want that the sum of absolute values of rows should become 1. For example, if all are some kind of probabilities of mutually exclusive events, right? So in that case, the sum of probabilities should become 1. Or if all are some percentages in different say examinations. So suppose this is first terminal examination mark, second terminal examination mark, and third terminal examination mark, and you want to find the percentage of percentage marks scored in each, and the total percentage is 100%. 100% means 1. So at that time you will use this. So probability or percentage, then you will use L1 normalization. And similarly, if you just want to find what is the max value in each observation, sometimes you need to find. And remember, these are just 2 observations, but sometimes there are 100 columns. So that means this vector would be pretty long. And similarly, there will be thousands or millions of rows. So you have to find the maximum value for each of this column and each of the row. So at that time, it is better to apply max normalization, because the biggest advantage of normalization, or even this, that is this scaling, etc., is that when you change the values in the column or row, then the data distribution, underlying data distribution, does not change. So that means whatever assumptions you have taken for the original values, same assumption you can use for the new value. Okay. So this goal you must remember what is the goal and accordingly what kind of normalization you will use, right? Now this is a little bit detailed discussion that first, for example, L2 normalization, it's detailed discussion. So suppose I take one this kind of 3 column data set. This is the index. So it is not part of data set 0, 1, 2, 3, but this feature 1, feature 2, and feature 3, and these are the values. Okay. Then I want to apply L2 normalization. Now I know that every normalization means each observation divided by some magnitude. But if I want to apply L2, then what will be the magnitude? Magnitude will be Euclidean length of each vector. So what will be Euclidean length of first vector? Under the root 3 square plus 4 square. This will be under the root 1 square plus 0 square plus 5 square. This would be under the root 4 square plus 2 square plus 3 square. And this would be under the root 5 square plus 6 square plus 8 square. So that is what I have calculated first. That is that Euclidean length for each row is also called its L2 norm. So for this row, it is L2 norm is this, and therefore each value of the observation will be 3 divided by 5, 4 divided by 5, and 0 divided by 5. So that means now the normalized row has become 340, has been converted into 0.6, 0.8, and 0. And this is a unit vector. If I find its magnitude, it will be a 1 unit, right? Similarly, the second row was 105. So its magnitude or norm I have to find, and its norm is under the root 1 square plus 0 square plus 5 square, or that is root 26, and therefore each value will be 1 by root 26, 0 by root 26, and 5 by root 26. Again, that would be a unit vector. If I find the magnitude of this, that would be 1 unit. Next is 4, 2, 3. So L2 norm is under the root 4 square plus 2 square plus 3 square, or square root of 29. So these will be 4 divided by root 29, 2 divided by root 29, root 29 is this value, right? And 3 divided by root 29, okay? And so the row which was originally 423 will become normalized like this, okay? And then this row, so that would be 5, 6, 8, and then that would be under the root 5 square plus 6 square plus 8 square. And that norm would become root 125. So that will be 5 by root 125, 6 by root 125, and 8 by root 125. So original data set, which was this, that is 340, 105, and 423, 568, that has now been converted into this 0.6 point and all that. So you can see that the values have completely changed, right? But this, what I said is whatever is the data distribution, if I plot the KDE plot for this data set and KDE plot for this data set, then they will be exactly same. Histogram, everything, box plot, everything will be same for this data set. Okay. So nature of the graphs will not change. Data distribution will not change. Only the scales have been adjusted. Okay. Now L1 normalization, same thing again, each observation divided by magnitude, but this time the magnitude is the sum of observations. So here the observations are 340, so the magnitude will be 3 plus 4 plus 0, 7. And therefore this 3 value would be converted into 3 by 7, 4 by 7, 0 by 7. Here the row is 105, so the magnitude is 6. And therefore 1 by 6, 0 by 6, 5 by 6. Here the magnitude is 4 plus 2 plus 3, 9. So therefore 4 by 9, 2 by 9, 3 by 9. Similarly, here the magnitude is 5, 6, and 8. So that is sum is 8 plus 6, 14 plus 5, 19. So 5 by 19, 6 by 19, and 8 by 19. So this is the normalized L1 normalized row. Okay. So original data frame was this kind of data frame, this, and the new data frame after L1 normalization is this. But again, data distribution and everything remains same. And then next normalization, again it is very simple, that each observation divided by the maximum value in that vector or that row. So that means if this is the row 340, then the maximum will be 4. So all observations should be divided by 4. So 3 by 4, 4 by 4, and 0 by 4. And therefore, whatever was the largest value, that would be converted into 1 in the max normalization. Similarly, here the 105, so the largest value is 5. So divide everything by 5. And therefore 1 by 5, 0 by 5, and 5 by 5. So this will be the normalized value of this row. And similarly, second row, third row, you can calculate each row's normalized value by this kind of calculation. And this is the original was this data frame. These 3 columns were there. This is index column, remember. So then new value of that same data frame is like this. So we say that it has been max normalized. Okay. And here the maximum observation of the original vectors become converted into 1. So this has been converted into 1, this has been converted into 1, and here this has been converted into 1, and here this has been converted. Now the question is, will we do this kind of normalization by actual calculation this way? Because you can understand the problem that here it is a simple data set, so I could do it, and still I needed to calculate the square root and this 3 by 7, so I needed to calculate it, which would require a calculator and all. So we don't do it by that way, but we rather apply normalizer. That is from standard sklearn.preprocessing, import normalizer, then we create a normalizer object, and then we actually just apply that normalizer object, normalizer.fit_transform to my data set, and that will give me the normalized value for whole data frame. Okay. So obviously we will not calculate things manually like this. For example, the same data frame, this same data frame, originally it was this data frame 340, 105, 423 and 568. So let us create the same data frame 3403. This because this dictionary method, you know that this will become the column names, and this will be the value under first column. So if I horizontally want to look a row, then 340, that will be the first row, 105, that will be the second row, and so on. Let us create a data frame, and this is my data frame 340, 105, 423 and 568. While this is that index column, right? Now I want to find L2 normalized value of these all observations, L1 normalized value also, and max normalized value also. So will I do all these lengthy calculation? No. I just import from sklearn.preprocessing, import the normalizer. The next step would be normalizer object. You will define with each different type of normalization. So normalizer 1 object is created with normalizer in bracket norm equals L1. So L1 norm, then normalizer L2 is equal to normalizer norm equals L2, and similarly normalizer max is equal to normalizer in bracket norm equals max. And this you know don't need to remember. You can just write normalizer and then put a question mark. Then the documentation you can see that what are the possible arguments. So these are the three possible arguments and that we are creating. But this is just created the normalizer object with each type of norm. Now you have to apply that normalizer object to your data. Data here is the data frame. This. Okay, so then for that you have to do this. First look only this much, don't look out of that. So only this much. So normalizer underscore L1 first normalizer dot fit underscore transform and data, right? Similarly normalizer underscore L2 dot fit underscore transform and data, and similarly normalizer underscore max dot fit underscore transform and data. So this helps in getting the normalized value. But then you have to give some column header to the normalized value. So here what was the column header? Then feature 1, feature 2, feature 3. So here also I will give same column header, data.columns, data.columns and data.columns. So that will have feature 1, feature 2 and feature 3. But as is the problem with most of the things in sklearn library, that whatever the results are obtained, they are not in the form of pandas data frame. So once this much is done, normalization is done and column name assigning is done. This again second type of normalization is done and column name are assigned. The third type of normalization is done and column names are assigned. Then you just have to write pd.data frame, right? And once you write pd.data frame, then you can easily convert this into data underscore L1, data underscore L2 and data underscore max. So that will give the normalized data in the form of pandas data frame. Okay, and these column names you are writing feature 1, feature 2 and feature 3. So if you want to add some suffix just to distinguish, then for data underscore L1, this is L1 normalized data set. So each column's name would be attached with a suffix underscore L1. Similarly for this pandas data frame, which is L2 normalized data set, every column name would be attached a suffix underscore L2. And similarly for this data frame, its column names would be converted into these column names, so that every column name would be attached a suffix max, just for the sake of further clarity. Now we concatenate all these data frames. So that is data normalized, L1 normalized, L2 normalized, max normalized and the original for better comparison. With axis is equal to 1 means side by side concatenation, so that the number of rows will not increase but number of columns will increase. It will become wider data frame, resultant data frame will be wider. And if I execute this, first let me clear that so that you can be satisfied that and if I execute this, then this was my original data, this is my L1 normalized data, and you can see that when we calculated mathematically, then also we got the same for L1 normalized data somewhere here 0.4286, 0.5714 and 0. So here you can see 0.42857, that is 865714 and 0, right? And so on, you can check each of these. This is L2 normalized data, these three columns, and this is max normalized data. So you can get all three kinds of normalization in a single piece of code. And you can see it's not even difficult code because it is highly repetitive. So once you write the code for L1 normalization, then write the data creation, add column suffix for only that. And once you do that, then you can just copy paste that row with here and write L1 is replaced by L2, and here L1 and L2 they are replaced by max. Similarly, suffix also ultimately they are replaced. That is all you have to do. Otherwise, very simple. Create a import normalizer, create normalizer object with corresponding norm, and then normalizer dot fit transform, and decide some column names which you want to apply to that new pandas data frame. But also remember that this whole thing will not be a pandas data frame, so you have to convert your result into pd.data frame, right? So that is okay. And here I have written from this point onwards, the discussion of part B. Part B is we are doing this scaling techniques, standard case scaler, min-max scaler, and the normalization. So normalization was new, but rest of the things are repetition of chapter 12 discussion, and that I can show you also chapter 12 here, because some may feel it is coming out coming from so far away. So yeah, it is there, but you can see that this is the difference between normalization and standardization. Difference between then when to use normalization, when to use standardization. Here, this word normalization means min-max scaling, and when to use standardization. Okay, and pros and cons of min-max scaling and standard scaling, and all those things where they are applicable. Same thing here, where they are applicable. Okay, what are advantages and disadvantages and all those things. So that means here this discussion is over. Okay, what are the common pitfalls or common sources of error, and how to avoid them while normalizing or standardizing the data. Okay, among them, and this is very important, so don't think that just because I'm saying we have already covered in 12th chapter, you will also pass through this saying that we have already covered in 12th chapter. No, please visit 12th chapter, listen to the lectures, because for example, this data leakage. Now this data leakage is so big mistake that uh, that it will mess up with your entire machine learning model completely. Okay, and it will make the results completely unreliable, right? So this is what you want to do, what you should do. So don't just pass like me that we have already done in 12th chapter. Actually open the lectures of the 12th chapter, listen to those lectures once again, and go on understanding each point of these many topics. Not much it is, but maybe you should require it. And this part now we will be doing introduction to feature selection techniques, because our chapter 22 has first part creating new features, second part data scaling and normalization, and now introduction to feature selection techniques. The techniques are broadly classified into filter methods and wrapper methods. So that we will do in the next lecture. Thank you.